Welcome to another podcast. This episode we're going to be taking a look at how to apply the lessons we've learned about equivalence relations and equivalence classes to counting what are called ordered partitions. Now I'm going to introduce this concept with an example first, and then we're going to talk about some of the definitions involved here and introduce a counting formula at the end of the video. So the particular question that I'm interested in for now is how many ways are there to pick 4 different committees of size 3, 5, 5, and 7 from a group of 20 people. So let's analyze a couple of things here about this before we jump into trying to find the solution. The committees are different, meaning that they are distinguishable. So I have a committee 1, a committee 2, a committee 3, and a committee 4. And what I'm looking to do is just take 20 people and divide them into these 4 basically slots, if you want to call it that. So we're going to try to distinguish it from slots because we use that sort of imagery when we were talking about multiplication rule. So I might use the term bins, like a trash bin or a waste bin or something like that. We're basically trying to put a collection of things into each group rather than just one thing into each slot. Essentially, this is a partition, and what we're going to be doing here is counting ordered partitions, and order implies that the committees are different. If the committees were all the same, then this is a very different problem, and we can talk about that. Another thing here is that hopefully it's clear that the order within each committee is not important. So if I choose 3 people to be in committee 1, it doesn't matter the order in which I put them into committee 1 because at the end of the day they're still the same 3 people. But it does matter if I switch committee 1 and committee 2 because then I have the wrong size for committee 1 because it's supposed to have size 3, and whatever people I chose to be in those would get switched. If I intended for them to be in committee 1, they'd be in committee 2. So I'm thinking of the 4 committees as being different committees, so it matters if I switch their orders, but within each committee the order is not important. So how would we go about solving this? Sort of the first thing that I can think of here is why don't we just line up all 20 people. So say I was trying to make a decision here. I'm going to line up everybody. How many ways are there to do that? Well, since it's 20 people, there are 20 factorial ways for these people to line up, one after another. Okay? The second thing I might do then is just sort them. So sort based on order. And what I mean by that is the first 3 go to committee 1, the second 5 go to committee 2, and so on. So I basically, if you want to think of the sorting hat from Harry Potter, I'm basically sorting everybody into their houses. Now, it's just based on how I initially lined them up. But here's the thing. Within each committee, it doesn't matter. So these 3 people that go to committee 1, how many people am I actually counting in this 20 factorial? Well, 20 factorial counts every possible way to line people up, and in particular, it rearranges those first 3 people 3 factorial times. So within each committee, committee 1, there are 3 factorial possible rearrangements just for the people I put in committee 1. Committee 2, because it's got 5 people, have 5 factorial possible arrangements. Committee 3 will have another 5 factorial possible rearrangements. Committee 4 will have a 7 factorial possible rearrangements, and none of these should factor into the count. Right? So I count 20 factorial ways to line people up, but a great number of those 20 factorial rearrangements include rearrangements of just the 3 people in C1, just the 5 people in C2, and so on. And there are 3 factorial, 5 factorial, 5 factorial, and 7 factorial possible rearrangements. This leads to an answer of the following. The answer here is take all 20 factorial and throw away, that's what we mean when we divide numbers in mathematics, throw away or partition off the 20 factorial into groups of 3 factorial, 5 factorial, 5 factorial, and 7 factorial that no longer add to the overall. Basically, it's saying that the 3 people that ended up in C1, I can rearrange them in 6 different ways, and I should divide whatever answer I get by 6 because I've counted 6 times too many. The same thing for 5 factorial. 5 factorial is 120. I've counted 120 too many rearrangements by factoring in the possible rearrangements of just C2. So I basically take everything and arrange it, and then I throw away the individual groupings that are rearranged. So that's our answer. And the question here is, how does this tie back into the idea of a partition? How does it tie back into what we've been talking about so far? Well, I can think of the committee for this particular example as being sort of synonymous with or equivalent to the concept of an equivalence class. And when I do that, that immediately imposes a relation. So I can think of the equivalence relation as being the relation belongs to same committee. So I've got a group of 20 people, and I'm going to impose the relation on them belongs to same committee. In other words, you're related to someone if you're on the same committee with that person. That then forces the committees themselves to be equivalence classes. And what we've talked about in previous videos is that the equivalence classes form a partition. And so the committees form a partition of the 20 people into groups of 3, 5, 5, and 7. And essentially what we're trying to do at this point when we count is we're trying to figure out how many different partitions are possible. So this counting question is logically equivalent to how many partitions of size 3, 5, 5, and 7 are possible on a set of size 20. In other words, how many ways are there to divide 20 up into 3, 5, 5, and 7? That's essentially what this question is asking. And so we have a counting formula that covers just that scenario. So the counting problem that we're looking at here is a problem called counting ordered partitions, and I wouldn't worry too much about the word ordered there. Ordered just implies that there's an order to the committees, like the committees are all different. That's what it means by ordered partitions. So the theorem here is, let's let A be a set with n elements. Then suppose n is equal to n1 plus n2 plus nk. In other words, we've decomposed n into a summand. So for example, in the committee problem, we decomposed 20 into 3 plus 5 plus 5 plus 7. Now I realize that's not unique, so I'm just supposing that that's what it looks like in this particular case. So if that's the case, then what we have is that there are n factorial divided by n1 factorial, n2 factorial times all the way down to n sub k factorial. That's how many partitions. There are this many partitions of the form A1, A2, so on to AK. These are the parts. Let me just do it this way. Partitions with parts A1, A2 to AK, where the size of each a sub I is equal to n sub I for I equal to 1, 2, all the way up to k. Basically what this says is that the size of each part is congruent with the size of the decomposition of the total size here. So I'm basically dividing the set A up into parts n1, n2 to nk. I'm dividing up into k parts. They don't have to all have the same size, but based on the sizes they have, this is how many ways to do that process. And so this is the counting ordered partitions problem, and the committee example here I gave is a great thing to sort of have in the back of your head to remember how to do this process. This is related to equivalence relations and equivalence classes, as you can see, but sometimes it's harder to pick out that relationship than it is just to apply this formula. So the thing that I really want you to leave this video with is an understanding of how to use and apply that formula. And we'll talk more about using it in class. All right, thank you for watching.